If you remember that at a particular temperature, the average kinetic energy of a gas is related to the temperature, and so it turns out that we can discuss the concept of the average velocity of a gas molecule. And so a useful relationship is the so-called root mean square speed of the gas molecules, which is given the symbol of u here in this equation. In essence, then the root mean square speed is related to the root of 3 times the gas constant times the temperature divided by the molar mass of the gas. So there turns out to be an inverse relationship between the molar mass of a gas and its speed. In other words, as the molar mass goes up, the speed must go down, and there is a direct relationship between the root mean square speed and the temperature. In terms of the value for the gas constant, we typically use 8.314 joules per degree Kelvin mole, which is, in terms of the base SI units, the same as 8.314 kilogram meter squared per second squared Kelvin mole. Therefore, you have to remember that the molar mass has to be in kilograms per mole, not grams per mole, and the temperature is in Kelvin. As you see here, there is a distribution of molecular speeds that occur for a particular gas at a given temperature. And in this plot, you see the molecular speed plotted on the x-axis and the relative number of molecules at a particular speed on the y-axis. This is a plot for some gas at 0 degrees Celsius. And so if we were to calculate the root mean square speed, we could plot and put this on the graph, and we see that in essence this is represented by the dashed line that you see here. And so if we go to some higher temperature, the distribution flattens out a little bit and for 500 degrees Celsius, but you see that the maximum number of molecules has moved to a higher molecular speed. And so if we calculate our root mean square speed at this temperature, obviously the root mean square speed has gone to a higher speed. So the important point here is that if we consider two different gases, these are real gases, the lighter gas with the smaller molar mass will have a higher overall average velocity than the heavier gas. And so likewise, the lower the molar mass, the higher the root mean square speed. So shown here is a plot of the distribution at a particular temperature for the molecule O2, and its molar mass is 32 AMUs, and if we compare that to nitrogen, the distribution moves to slightly higher average speed, and because the molar mass is lower. If we go to something like water, it moves even higher because of the lowering of the molar mass. We go to helium, we have a pretty significant increase in the average speed, and then finally we go to the lightest of the gas molecules, elemental hydrogen, which then has the distribution you see here, with the average being at the highest of the molecular speeds. At this point, we need to consider the consequences of these changes in speed as an effect of the size of the molecule, and it's useful to discuss the concept of diffusion and effusion. These are very closely related phenomena, but not exactly the same. Effusion is a process in which a group of gas molecules, which are in a container that happens to have a hole in it, the effusion describes the rate at which the gas molecules are able to go through the hole and go into an empty space. So obviously, for this to occur, the random motion of the gas molecules has to at some point allow the trajectory of some of those gas molecules to go through the opening. In addition to this, then, the idea of diffusion is such that the gas molecules are spreading out throughout the container, and there is essentially a process which results from the random collisions and the passing through the space and to fill other voids or places where the gas molecules are not located. This diffusion process typically occurs when we have two different gases that are trying to mix with one another, and you have collisions between the different gas molecules. Just like we had in the root mean square equation, the rate of effusion is inversely related to the molar mass of the compound, and it is related to the root of 1 over the molar mass. And so we can write a relationship that describes the rate at which the effusion occurs for two different situations, or for two different gases, as you see here. And of course, these rates are proportional to or related to the root of the ratio of the molar masses. If we consider the process of diffusion, where a gas then spreads out into a container that has another gas, we have to discuss the possibility of other collisions. And so in this case, of course, the diffusion process is faster for lighter gas molecules than it is for heavier gas molecules because of the faster root mean square speed. However, the diffusion of a gas is slowed by the collisions with other gas molecules, and this causes the direction and speeds to change. The average distance that a gas will travel before colliding with another gas molecule is sometimes referred to as the mean free path between the collisions. And so this is sometimes used to plot the potential directions that an individual gas molecule can go during the diffusion process. At this point, we need to consider how a real gas behaves and how it might be different than the hypothetical ideal gas. We see here the ideal gas law, which is PV equals nRT. It turns out that this equation works really, really well at low pressures and high temperatures for most gases. However, for very high pressures and low temperatures, the real gases deviate fairly significantly from this equation. And so what we need to deal with then is a situation where we can understand what causes that to be true. So turns out that whenever a gas molecule collides with another gas molecule, we have been assuming that the molecules bounce off one another and are essentially totally elastic. But that's not totally true, and so in fact, while they're in contact with one another, there may be some sort of attractive force between the two gas molecules that causes them to stick for some moment in time at a given temperature. So that needs to be taken into account. The other aspect of this is when we have a very small container, we have to recognize that the molecule itself has a molecular volume, and so at some point when the molecules get pushed together to the point where they actually begin to touch one another, then the molecules will no longer be in the gas phase, and essentially they would change into the liquid or possibly the solid because of their occupying certain amounts of molecular volume. To account for these properties, a Dutch scientist named van der Waals came up with a mathematical modification of the ideal gas law to account for the interactions of the gas molecules with one another, both in terms of adjusting for the molecular volume and the intermolecular forces. So what he did is he subtracted from the volume a factor of n times b, where n is the number of moles of gas molecules and b is a constant associated with the particular gas in question that accounts for the volume of the gas molecule. Likewise, we also adjust for the intermolecular forces, and so in this case, the A is unique to the gas in question, and this affects then the is subtracted away from the nRT divided by V factor. And so in this case, then these two things taken together account for the data that we typically observe. These values of A and B for individual gases have been compiled in tables, and you have these available to you in the files folder of your Canvas course. A consequence of this is shown here in the plot of temperature for a particular gas as compared to the possible value of PV divided by RT for an ideal gas. For an ideal gas, the value of PV divided by RT would be 1 at all temperatures, and so you can see that as the dashed black line labeled ideal gas here. At different temperatures for a real gas, you're going to see significant deviations away from this behavior. The behavior at high temperature behaves fairly closely to that of the ideal gas, but as the temperature decreases, the average kinetic energy of the molecules decreases, and hence the collisions between the molecules on occasion can result in sticking, and so you see something as you see here in the green plot, where at the high pressures there's a really significant deviation to values greater than 1, but at low pressures the deviation is to values less than 1. If we then also look at several different gases, the lightest of the gases, hydrogen, behaves the most like the ideal gas, but as you go to gases with greater and greater molecular volume and significant intermolecular forces, then you get quite a bit more complex behavior. And this is all modeled quite well using the van der Waals equation.